So what is an empirical formula? Well, it might be easiest if we start with something we're a little more familiar with, which is a molecular formula. And we should be familiar with glucose, C6H12O6. And so the numbers here, the subscripts, represent the number of atoms that make up a molecule of glucose. 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. However, remember, they also represent the number of moles of atoms of each element that would exist, or that would make up a whole mole of molecules. Now, before we can come up with the molecular formula, people who are that are analyzing this compound were able to determine the percentages of carbon, percentage of hydrogen, percent of oxygen by mass. And then from those mass ratios, they were able to determine a mole ratio. And so the mole ratio originally for glucose was CH2O. Notice that it's the simplest whole number ratio of the number of atoms that make up one molecule. So what this tells us is that for every 1 atom of carbon, you would have 2 atoms of hydrogen and 1 atom of oxygen in a sample of glucose. So that would be the type of formula we would get to before we got to the actual molecular formula. This CH2O, would be the empirical formula for glucose. And again, remember that the original one we had here is the molecular formula. Which would actually come in the next segment, where we're going to take the empirical formula and try to figure out what the molecular formula would be. But just so you get kind of an idea of what the empirical formula is. So let's take a look at an example. Here we have some data that was obtained in the field. We have the percent phosphorus and the percent oxygen in a compound that contains just those 2 elements. Well, obviously what we're trying to get to is the formula for this compound. So we need to know what the subscripts are for the phosphorus and oxygen. Now, those subscripts represent a ratio of either atoms or moles of atoms. They don't represent a ratio of percentages, so I can't take the percentages and plug them in there. They also don't represent a ratio of masses, so I can't use masses. But I do know that if I have masses, I can get 2 moles. So what we want to do is take these percentages and somehow get to the mass of each element. And the way we're going to do that is we're going to assume that we have 100 grams of this compound. If we have 100 grams of this compound, using the percentages, we could then say that we have 43.6 grams of phosphorus, and we would have 56.4 grams of oxygen. Now again, the mass isn't going to do us any good. We can't plug that into our formula. However, we can plug in the number of moles. So what I'm going to do is I'm going to convert each of these to moles. So we use our periodic table, and we're going to convert our grams to moles. Oops, excuse me. And that gives us 1.41 moles of phosphorus and 3.53 moles of oxygen. Okay. Now that's not bad. I mean, at least now we have a mole ratio. So we could go ahead and try to put that in up here, 1.41 and 3.53. But we see that, that the numbers that we use for subscripts have to be whole numbers. So we have to get rid of these decimal numbers that we're getting from the data here. The way we're going to do that, or the first thing we're going to do to try and get rid of decimals, is divide by the smallest number of moles. So we're going to divide by the 1.41, and at the very least, that's going to change our moles of phosphorus to 1.00 moles of phosphorus. And when we do that for the oxygen, we end up with 2.50 moles of oxygen. Now it gets us closer. We're still not in whole numbers, but at least now we can kind of see that there's an easy solution here. We're going to take both of these numbers of moles and we're going to multiply by 2. So if we multiply by 2, we end up with 2.00 moles of phosphorus and 5.00 moles of oxygen. And so now we can go back up to our formula and we can plug those numbers in. So phosphorus 2, oxygen 5. So the formula we would have for this, the empirical formula, would be P2O5. Now it's important to remember that this is not the molecular formula, this is the empirical formula. The molecular formula would have to, or this could be the molecular formula. The molecular formula may also be some multiple of that. So it could be P4O10 or perhaps P3O15. You get kind of the idea there. So this is the process that we would go through then for an empirical formula problem. The part that we need to get to is this, these moles. Okay. Where you start could be different. You could start with grams. Most of the time, if you're analyzing the compound, you can start with grams. But occasionally, you might start with number of molecules or something different. So, but it's important to remember our mole conversions and that whatever data we're starting with, ultimately we need to figure out the number of moles of each element that's present. We'll do one more here. In this situation, we're told that we have 11.90 grams of a compound, and we're analyzing that to determine the empirical formula. We know that of the 11.9 grams, 6.3 grams is carbon, and the rest is oxygen. It wants us to figure out, again, the empirical formula. So we know that the compound contains carbon and oxygen, right? So we're trying to figure out the subscripts in the empirical formula. We know that there is 6.30 grams of carbon, and by subtraction, then we can calculate that there are 5.60 grams of oxygen. Now, no need to go, to think about percentages here because we can go right from grams to moles. So we've got our 12 grams of carbon to 1 mole of carbon, and our 16 grams of oxygen to 1 mole of oxygen, which gives us 0.525 moles of carbon and 0.350 moles of oxygen. Okay, again, remember from the last problem, our first step is going to be divide by the smallest number of moles, which in this case is the oxygen. So we're going to divide by 0.350. The carbon is going to come out to 1.50 moles of carbon. And of course, the oxygen will come out to 1.00 moles of oxygen. Like with the last one, we can basically multiply both of these by 2, which would give us then 3.00 moles of carbon and 2.00 moles of oxygen. And so our formula, our empirical formula, would be C3O2. Now, these are two examples where there are only 2 elements. There can be 3, 4, 5 different elements present, and you would basically go through the same process. Divide by the smallest number of moles once you got to moles, and then you take a look at, if it didn't come out to whole numbers at that point, you would think about multiplying by 2, 3, 4. Very rarely would you go beyond 4 in any of the problems that we have. But in real life, you could go beyond that. But most of the ones you'll see in chemistry class, you would at that point, if you got to the point where you were multiplying by 4 and it wasn't coming out right, you probably had done some other calculation incorrectly. All right, so what we need to do is just practice some of these. So make sure that you're doing some practice problems of different empirical formula calculations.